As we mentioned, we will move on to the next session. We have with us Mr. Tathagata Chakraborty, Technical Manager, Sunanda Environmental International Private Limited, and Dr. Debolina Sengupta, Associate Director, Teas Gas and Fuels Research Center, WEF Nexus Coordinator, Texas A&M Energy, USA. So we would request Mr. Mukherjee and Dr. Sengupta to please join us, and we would request Mr. Arun Mukherjee to please take the session forward. And we believe we have Dr. Padmavati and Professor Banerjee, Rintu Banerjee with us to share their observations at the end of the session. Thank you. Mr. Mukherjee, sir, Arun sir, you are on mute. You'll have to unmute yourself.
Yeah. Good afternoon, and I would like to extend a warm welcome to Mr. Tathagata Chakraborty and Dr. Debolina Sengupta. This session is about sustainable approach to industrial water management and maintaining WAS. Water is as important to the world's economy as oil or data. Though most of the planet is covered with water, more than 97% of it is salt water. Fresh water accounts for the rest, and most of it is frozen in glaciers, leaving less than 1% of the world's fresh water available to support human and ecological process. Every year, we withdraw 4.3 trillion cubic meter of fresh water from planet's water basin. We use in India about 90% of the fresh water in agriculture and 2% for the industry. Of late, the highly water consuming agriculture producers are getting restriction in production, or the products are getting diverted for energy support like ethanol from maize. Business can play a leading role in mitigating the water issue to limit not just their own risk of sustainability and survival, but also the risk of all stakeholders relying on these systems. This can be accomplished by directing action through three spheres of influence: direct operation, supply chain, and wider basin health. All industries rely on water some way. An industry's water footprint can be seen in 4 key areas of its value chain. That is raw materials, suppliers, direct operation, and product use. For example, a metal and mining industry need water for dust control, drilling, washing, processing, and transporting in slurry form. But the major challenge lies in availability of fresh water in the basin. Water level is going down, impurities are increasing, and particularly in the coastal area like Haldia, ingress of salinity is increasing. This problem is happening globally, and World Bank estimates that this water crisis could slow GDP by 6% by 2050. 2/3 of the business have substantial risk in their value chain and direct operation. Industries will face the challenges in 4 forms: physical, regulatory, reputational, and stakeholders. Industries approaches of reduce, reuse, and recycle the water in their processes. These approaches are creating a new process and improving resource efficiency. Many industries are including water use as key performance indicator, KPI. The reduction in water usage ultimately reflects in their productivity and profit line. We know that in cooling tower application, already air-cooled towers are getting installed for saving of water. For the supply chain, three critical levers to pull: reducing energy use and shifting to renewable, and implementation of reduce, recycle, and reuse in their process of application. Already, we have seen the regulatory framework from Pollution Control Board has established the norms of zero discharge and also the norms of discharge of wastewater quality from individual industry, which will finally help in sourcing of the fresh water quality for safe drinking and eliminating contamination in the fresh water and the basin. In Haldia, the water level has gone down by about 10 meters and affected the water quality. Salinity now is around, in some area, around 4,000 ppm. TDS varies between 1,000 to 3,500 ppm, which was earlier around 750 to 1,200 ppm. These variations of parameters required retrofitting of existing pretreatment of plant and also additional capacity to be added for maintaining the throughput. The quality deterioration in the fresh water also resulted in reducing of the capacity of the wastewater plant. The utility industries now putting up supercritical, ultracritical power plants with higher efficiency, which also reduces the water consumption per megawatt hour of generation. The energy transition to renewable energy will also help in water conservation. We are confident that the industries are already playing their responsible role, as the presentations were made by Indian Oil and Haldia Petrochemical and other industry for optimum water utilization, and with the technological advancement, further improvement will happen. There is a need at this stage of a very active collaboration with local and global academic institutions and investment in R&D for technological improvement, for adopting the best practices in the process of any industry. It's heartening to see that already the large industries around Haldia are participating in the PAT scheme, by which it is expected that the specific consumption of every resources will be optimized. Today, the water management is an essential business priority in industries. However, self-regulation and compliance will be the key for industry for their sustainability, development, and social development. Thank you. With this, may I now request Mr. Tathagata Chakraborty to share your views.
Hello.
Tathagata.
Yeah, thank you, sir. Thank you, sir, for letting me in. The first thing I would like to get confirmed with is that am I clearly audible or not?
You are.
Okay. Thank you, sir. So, good afternoon, ladies and gentlemen, and thank you for giving me a window in this platform. I would like to keep it short and crisp, because most of the kind of problems and most of the things which we should be concerned with have been correctly highlighted by Professor Arun. So the thing is, like I was unaware of the fact that about the changing quality of water in Haldia region. Like the TDS has been, has been increasing from 700 or 800 ppm, kind of in the range to 3000 or 4000 ppm, which is kind of 10% of the TDS we get in normal seawater, which is very, very alarming. The topic is about sustainable water management in industries, and I've been listening to the conversation for quite some time now, and a lot of industrialists have spoken, and I've gathered a lot of knowledge from that. Thank you so much. So, according to a bit of research that we have done, but before that, a bit of background about what we do generally. We are a very young company, not even a decade. We are into the kind of water and water quality domain. So, as far as my knowledge goes, there are two paradigms of looking at it. First of all is diagnosis. First paradigm is diagnosis. The second is solution. Diagnosis is water quality analysis, that what is actually what are the constituents or what are the parameters of water that we should be concerned with, even if we are using it for industrial purposes or drinking. So far, in our 7 or 8 years of operation, we have concentrated on drinking water quality. We are in association with various state governments, and we completely manage the water quality of these state governments all over the state of Bengal. And so basically, we have been concentrating on drinking water quality and drinking water quality management, and kind of collaborating business intelligence with water quality. I'll when I get the, may I request a screen sharing so that I can, in the later part of my conversation, go and hello.
Yes, Tathagata, you are co-host, so you can share your own screen.
Right. Okay. Thank you. So, getting into the industrial part, so far, I mean, my research has led me to the fact that there are certain industries which consume most amount of water on an average, starting with definitely the agriculture industry, the horticulture industry, the food production. But that is an essential industry. We cannot kind of neglect that. So that consumes the most part of water. Next is garments and textiles. That comes second in terms of water consumption, like the clothes and garments we wear. Followed by meat production. This is another kind of semi-essential industry which consumes a lot of water. Then comes the beverage industry, followed by the automobile industry, and obviously thermal power plants. So these consume a lot of water. And basically, when we talk about water, we generally talk about groundwater, which is a rapidly depleting resource, as pointed out by Professor Arun already. So the population and the demand of the population is increasing, 7.2 billion and counting, but the resource is constant and is depleting. The most alarming part is that if industrial water is left untreated, 1 liter of water has the potential to further contaminate around 8 or 10 liters of water down the line. So basically, it's not about how much water we are using in the industries and kind of disposing of in the environment. It's about what the effect, what is the kind of magnification it is having in the environment, because 1:10 ratio is being followed, or 1:8 ratio is being followed. 1 liter of water has the potential to contaminate around 8 to 10 more liters of water in the environment. According to national water footprint recent data, India is one of the biggest consumers of industrial water, left behind by highly industrialized nations, of course, like China, United States, and few South American, Latin American nations, and Russia. So this is basically the problem. So what I understand from my kind of uh, association with this domain is that the effort needed to curb this is, first of all, awareness. We need to recognize, we need to make peace with the fact that what we are the rapidity at which the resource is getting depleted is something which we are may not be able to fathom with. It is actually maybe far graver than we can actually imagine or fathom with. And the next is Professor Arun rightly said, he mentioned the word retrofitting. So in industries, when kind of old and outdated equipments do consume a lot of water, when we go for retrofitting, we even in terms of government schemes, I've seen this, like water supply schemes. So if the schemes, certain parts of the schemes are old and outdated, we have seen that in the design, if the design has been like into it practically, the last census in India was taken in 2011. When we design a scheme, what we keep in mind is how much population we need to cater to in terms of supply of water, and we design the scheme accordingly. And definitely we keep in mind that, okay, in 2011 a particular village or habitation is having a population of 100. In 2021 it may rise up to 1,000. So we need to cater that population also. So we need to kind of do our mathematics of water supply accordingly and increase the volume accordingly gradually. So but kind of even our calculations have been failing these days, because a lot of when government of India has taken up a project called FHTC. A lot of you have may be aware of that, the functional household tap connection, Har Ghar Jal Har Ghar Nal. This is one of the primary propagandas of the government, that every single household should get access to clean water. According to the National Jal Jeevan Mission, which is the water management wing of the government of India, the project is known as Har Ghar Jal Har Ghar Nal, and it's called FHTC, functional household tap connection. So we are running a lot of ground surveys all over West Bengal in this particular for implementing this particular project. And we have seen that although the schemes that we have we had designed a long time back to supply water to the farthest and most remote portions of West Bengal particularly, there are a lot of pockets where water is not reaching, even though our designs were flawless. That is because somewhere water loss, some retrofitting and is necessary. Equipments have worn out, so we are losing a lot of water in terms of transport, in terms of kind of operation and maintenance. So that definitely the first thing is awareness. We should recognize that we are running out of our resource. Second thing is retrofitting, and the main thing, which is the third point which is required, is recycling and kind of treatment of water. I like efficient effluent treatment plants and water treatment plants are the need of the hour for huge industries, and these should be working, and we should actually kind of focus on maintaining these. So water and regarding COVID, I was kind of mind blown to see the precautions that industries have taken in terms of COVID. So we have been following the COVID situation related to water right from the beginning. And it was, the main, sources of transmission of the viruses, droplets and all. But we have been monitoring the spread of COVID virus through water. And the first of such studies came out in Western Europe, in Netherlands, and simultaneously in Australia in March 2020, where the traces of this COVID virus was found in wastewater. And as if I'm not very mistaken, a similar study has been taken up by IIT Kharagpur also recently, that if we can find traces of COVID, this virus in wastewater, this is kind of a signal. This is kind of a this kind of a impending kind of what do you call, like say harbinger, that maybe somewhere inside the population of that in the vicinity of the treatment plant, or the area, maybe somewhere some hidden infections have taken place. So we have been following this also, and we are trying in lines of developing something to rapidly test water for COVID samples. And we have not come out with a complete solution of it, but we are in line with it. So this is basically my views over it. And if I can share my screen, I would like to end this by showing that how we have actually collaborated water quality data with business intelligence tools. Okay, so Sushmita ma'am, can you guide me on how to, I've this.
Yeah, can you repeat?
Yeah. I got it. So is my screen visible?
Yes, yes.
Okay, great. Okay, so this is my screen visible now?
Yes.
Yeah, okay. Okay, so this is basically a dashboard. We have our in-house information technology IT team where we kind of play with water quality data. We have a lot of data because we have been working in this domain for the past 6-7 years, so we have gathered a lot of data. This particular data set, this is a dashboard. We call this a dashboard, and this is a data representation. So what you can see in the screen is, this is live actually.
Can you share as a presentation, Tathagato?
I haven't made a presentation. Actually, this is live. What you're seeing right here is live.
Okay, fine.
This is live.
Okay, fine.
Yeah, so this is the dashboard. This is a demo dashboard with live data. As you can see, this is live water quality data that we have gathered from, if you can see the bar.
Folder is visible, not the actual screen.
Pardon?
Your folder is visible, not the actual application that you want to show. If you share the application, I think that will be easier for us to see.
Actually,
We just see your
can you see? Can you see the graphs and all the?
No.
No.
See a folder.
Only the folder.
Yeah. So when you share your screen, if you're doing a share screen, then just minimize the folder maybe.
Now, how about now? Hello?
No.
Okay,
No.
just a second. My screen sharing somehow is paused. Why is it resume share? Is it visible now?
No.
Just a sec. So what is visible now? Only the folder.
Only the folder.
If I minimize it. Doesn't Zoom allow live screen sharing? Like, can't I share it? So is it only presentations or something I can share? Because I want to show it live actually.
You should be able to share your screen.
That's what I thought. How about now?
Yeah.
Is the graph visible? Is the screen?
Yeah, it is visible.
Yes.
Yeah, right. So this is the dashboard. Yeah, this is one of the dashboards that we work with, and this is for demo. As you can see, I have named it by my name only. So this is demo, but the data is live. So basically what we do is that we test water for different parameters, and that depends on the area where we are testing, right? So it can be heavy metals, it can be microbiological contaminations, can be BOD, COD, and you name it. So there are a lot of parameters that we test for. And what we have gathered from experience is that you keep on testing water and we keep on gathering data, but it doesn't make sense if you can't put it in a structure where you can make sense out of it. Like the data science and everything has been making a lot of hype over nowadays. So this is what we do. So over here you can see that we have tested for microbiological contamination, and this is the sanitary survey section. The wash section, we can now the sanitary survey, actually, to give you a brief idea about the sanitary survey if you're not acquainted with it, is that whenever we test, whenever you draw a sample from any source, be it a tap, be it pipe water supply, the surrounding conditions have to be taken care of. Like we have to record a complete set of 10-12 questions, and these are recommendations from the World Health Organization. Sorry. So and we need to kind of assign points, like if the answer to a particular question is yes, then there's 1 point, and if it is no, then 0 point. And the number of points a particular source gathers, the more risky is it. Like if we are collecting water from a hand pump, the question which comes into play is there a source of pollution within 10 meters of it? Why 10 meters? Because microbiological contaminations, general coliforms, fecal coliforms, which kind of contaminate the water from human feces or feces of animals, have a swimming potential of 5 meters. So who for safety makes it 10 meters? So if it is 10 meters, then you can be sure that the water from the source is not getting contaminated from a fecal source of contamination which is situated 10 meters away. So this is basically how we conduct sanitary surveys on ground. These are live results of live surveys, and the data we have taken, you can see we have the hospitals we have covered. If you can follow my cursor, the hospitals we have covered, we have taken total 8 surveys, and the low risk is 3, intermediate risk is 2, very high risk is 1. Very high risk is something when you get more than 80% out of 100. So this is how we plot the data. This is sanitary survey. Then we can also have a pie chart. The same thing we can plot in a plot in pie charts and all. Pardon my connection. Yeah. So likewise, and we have physiochemical data. So this is what we do. Generally, we have been doing for the past 6-7 years, is that we work with different entities in the domains of water quality, and we plot the data accordingly. So we have to. Is it visible, my screen?
Yeah, visible.
Yeah, right. So this is basically, and if you go to the these are the kind of all the sections where these are instruments, trends and charts. We are into trends and charts, and if we can go to analytical water quality results, the actually tabular results. Yeah, so this is, as you can see, 15 the water quality data has been collected on the 15th of Jan. Country is Yemen, not literally. It is not Yemen. We were testing the app, so we had to put different countries. We did this in India, not in Yemen. So location description, we have also a map view of it. This project actually is not running in Bengal right now. The Bengal dashboard is different. I'll show you. I'll give you a glimpse of it. This dashboard is running in a few parts of Africa. So this is the source image. You can actually record the image. So all this data you see has been collected. These are the parameters we test for. As you can see, got a parameter board over here. These are the parameters we test for in the physiochemical zone. Their microbiological analysis and sanitary survey, as I already explained. So this basically is it. And if to give a glimpse of, this is one of the achievements we got awarded by the government of India along with the government of West Bengal. This is the Koch Award we received for water quality management. We came second. First was I think Punjab. And is the presentation visible?
It's visible.
Yeah, right.
Tathagata, so, you run it first, please.
Pardon?
I said you run fast.
Okay, we're running short of time. Cool. Okay.
Yeah.
Okay. So the thing is, yeah. So basically, I'll wrap it up quickly. So these are the instruments we're talking about. So far, we have been talking about data and all the facts. These are the instruments that actually do the work on the ground. So as you can see, these are all live pictures taken, training sessions and all. Yeah, these are the instruments. We have got training sessions and all. So basically, we kind of manufacture some instruments. We kind of take technical support of other companies for some instruments. We train and we collect water quality data. and we kind of collaborate that with business. So this is the West Bengal dashboard. As you can see, some of it you can see there's red and greens. The reds are beyond permissible limit, and this is as you can see on the left hand side, the arsenic alert level. This is manganese alert level. So these are all, you know, kind of live water quality data where we have collected data from various sources of groundwater. These are all groundwater basically, and mapped it. These are the trends and charts we work with, as we have already shown. So basically this is the thing. And since we're running out of time, I'll not elaborate it anymore. I would like to wrap it up. And thank you everyone for being patient enough. Thank you so much. Arun sir, I'm done. Thank you. Hello. Hello.
Just a minute.
Thank you, Tathagata.
Thank you, Tathagata.
Okay.
It's
okay.
very interesting to have your huge data and the trend. But basically, what is interesting, or what will be interesting, is when this data is available to the authority, what corrective actions they have been taking, and if there is any follow-up done by you to check on those areas whether there is any improvement in the water parameter. Have you done any work on that?
Yes, absolutely. So as I said, that we are into the complete program system. Like when what happens is that we test the process is not a one-time process. It's a recurring process. Like each source, according to the guidelines of the government of India, each particular water source has to be tested at least once in a year, or best twice in a year. And we call these sessions pre and post monsoons, because before the monsoon and after the monsoons, the water quality trends change a lot. Some specific water quality parameters change a lot, not all. So yes, we do periodic inspections. There are lots of arsenic iron plants. Like if you see a water treatment plant or arsenic iron removal plant or a community purification plant in a particular area, the question is why here? Why has it been set up here? What prompted the government to set up a plant in this specific location and not that particular location? It is the availability of the data. When you have to arrive at a conclusion or a decision depending on live data. So that is the follow-up, and that is the action which has been taken. And to tell you the truth, we haven't been able to cover 100%. We haven't also been able to cover even 50-60%, but we are on the we're on the way, and we are hopeful.
Great. I'm sure you don't want to share the seriousness of the situation in terms of arsenic contamination in West Bengal. So I don't want to go into that. Thank you very much. May I now request Dr. Sengupta to please join us and share your thoughts.
Thank you very much. I would start by thanking the Bengal Chamber of Commerce for this honoring invitation. Thank you, Mr. Mukherjee, for conducting the session, and all the speakers that have spoken before me. So being the last speaker of this day, I think I have a responsibility of not only wrapping up my talk, but also wrapping up some of the thoughts that have been discussed in this session. So as has been mentioned, I am the Associate Director of the Tees Gas and Fuels Research Center and the Water Energy Food Nexus Coordinator at Texas A&M Energy Institute. So both of these center and the institute are associated with Texas A&M University. Just to give you an overview of Texas A&M University, since I also am the only academic speaker, I think it would be wise to give you an idea of where I'm coming from. So we are located in Texas. We are the largest state university system in the state of Texas. And also, we are the second largest state university system in the United States, with about 70,000 students enrolled last year. We create the workforce which serves the state and several parts of the country. And most of our graduates go to work within the state of Texas, where Houston is known as the energy capital of the world. Houston is very much industrialized. The entire Gulf Coast has very good access to feedstock of oil and gas, for which we are one of the areas which is heavily industrialized, and we see a lot of the nuances that you also probably share in the Haldia region as well as West Bengal. So with that background, since today the topic has been on sustainability, and sustainability has been my area of research. So I do work on research that goes behind sustainability in different aspects. But the way we look at sustainability is in a systems view, where we have interacting systems, and we have talked about several of these issues and topics in today's discussions. What we do is we quantify these and create the basic and advanced technologies and computational tools and methods so that we can make sustainability measurable. How do we measure sustainability? How do we measure progress towards sustainability? So those are the areas of research, and I'm just going to highlight a few of these today in terms of water. So at the basic, we have economy, which is the economic capital, the society, which is our human capital, and the environment, our natural capital. And we take the ecological goods and services for industrial development and societal well-being. Now, industrial development occurs where we create economic value for the society. We generate waste. Some of that waste goes back into that environment, and currently very little of it goes back into recycling and recovery. And of course, there is also human activities that create waste and also potentially impact the environment. So overall, one of the speakers before me said that sustainability is not only about environment. Sustainability is about a balance between environment, economy, and society, which I think was a very important distinction, and that needs to be noted as we go forward in terms of thinking and measuring sustainability. So given that background, we have to understand the scale of systems for sustainability considerations. And I'm sorry if I sound too academic, but this is the way we define sustainability so that we can translate the vision for world organizations such as the United Nations, their Sustainable Development Goals, of countries such as India, where they have the Swachh Bharat mission. How do we translate the vision into what we do as process engineers? As I probably mentioned, I come from an engineering background. I'm a chemical engineer by training. How do we link the information needed at global scales, and what methods exist in the academic community? So one of the things that I've observed is that we talk about the issues and problems in sustainability and sustainability managing options and opportunities. And there are several methods in which you can manage these things. But what are these methods at the leading end of academic community that can be translated and used for policy and business perspectives? So we need to understand that the sustainability is about systems. It is relative. It is a function of economic, environment, and societal parameters or indicators. And the scale of the system determines the nature or the set of the indicators that we use for sustainability analysis. And typically industries or businesses, we operate at sustainable technologies or the networks level. So that gives us a perspective. So next I will go into the topic of water. So as speakers before me have said, there is a great critical need for water. But where does the water come from and where does it go? So the water at a global scale, we look at water cycle. We have the evaporation from lakes, oceans, and streams. We have condensation, precipitation, surface runoff, and groundwater. So all of these are creating water. One of those is probably a river system, as I have shown here. Then we have the users of water, where we have geographical boundaries where we have rural and domestic livestock, we have public water supply, we have power generation and industrial use, or farmland and irrigation. And Mr. Mukherjee kindly gave some of these numbers in these areas that are used. So these are typically managed by local authorities and individual entities. And then we come to the industrial level, where we have business systems or water management networks. If you remember the scale of systems, this is the scale of a system where we have the water going into an industry and water coming out of the industry with interception methods. So what are interception methods? These are the physical and chemical processes that prepare the water for use in inlet or discharge into an outlet. And a very good example that was given is that if the water quality changes, this interception method will change. Either we are going to add a new interception method or retrofit interception method with which will help us to address the So one of the proposed methods of study that we have
Mr. Mukherjee, sir, you have to put yourself on mute.
So one of the proposed methodologies for study in this area from the academic community has been industrial ecology. And we have been at the leading edge of developing the theories and concepts of industrial ecology with process systems analysis. And we use energy, mass, and property integration methods with targets of minimum discharge, cost, and environmental compliance through mathematical modeling techniques and tools. This also creates potential for economic savings and anchor tenant approach for industrial ecology. I'll briefly touch upon anchor tenant approach in the next slide, but do remember the term of the anchor tenant approach. So we create these mathematical models and tools at a very greater level. And as I'll show you, these can be applied to different areas. So this is just an example of source interceptor sink diagram where we have the sources of water as groundwater sources, surface water sources, or reuse water. And there are primary users of this water: manufacturing, irrigation, livestock, mining, steam electric generation are some of the uses. And then after these use, there is a water treatment required. You cannot discharge this water directly into the public water bodies. So you have to put it through some sort of treatment system where you see pre-treatment, primary treatment, secondary treatment, and tertiary treatments. The tertiary treatments are typically the desalination technology. And then if you are going for drinking water, then you have to disinfect that before you can put it into further use. So here I'll briefly introduce you the mass integration, property integration, and energy integration methodologies. So mass integration typically deals with the total quantity of water, inlet and outlet from different industries. So you have a huge use of water in irrigation and steam electric generation, as has been mentioned. So there comes the quantity and integration of the quantity aspect of how much you are using. However, the property integration method looks at the quality of the water either at the inlet or outlet qualities. So the inlet and the outlet qualities are required to determine the type of process or processes that you are going to use for treatment of the system. And the quantity is very essential, is because the quantity is determined by the type of impurities or the type of things that are generated within a manufacturing process. Or in case of irrigation, if you are having the water mixed with fertilizers or other chemicals, then that changes the quality of the water and the property of the water. So you need to balance the inlet and the outlet of the quality of the water before you can discharge it, or before you can use it also in some of your manufacturing processes. For example, your boilers or your membrane systems require a certain quality of water, and it will not accept, there will be scale formations and other issues that will come up with your process system as a whole. So, for example, I've given here battery generation waste is water waste is different from refinery waste or petrochemicals wastewaters. So this is important, very important. Sometimes the property of the water or the quality of the water becomes more important than the quantity of water that is used, mainly because these properties of the water will determine the sustainability of local and regional water and the health, safety, and economic development for a region. And the third part, to do any of these technological interceptions, you need energy. So energy is a requirement for the process that supports water treatment. And these are typically in the form of utilities, either natural gas, coal, or your electricity. And these require operating costs. So anytime you have energy requirement that is coming fresh from an energy utility system, you have to have operating costs that are associated with it. So minimization of purchased utilities can be achieved by integrating with excess process energy that is currently wasted. So we have a lot of process energy waste, typically because it's low quality energy that is generated and there is no way to recover it. But there are newer methods in which we can recover those excess process energy and integrate it with your treatment systems, which effectively reduce the overall utility cost. So with that basic method explanation, I would like to go into the Haldia area region. So this shows a map of the entire entire Haldia zone, with the colors in purple being the existing industries right here. And there are other industrial zones where potential is there for future industries. On the right is a blow up of that inset, where you have the major industries, the dock, Haldia Petrochemicals, the Exide Industries, and also the Haldia Port as has been shown. So as we see here, we are in a zone which is surrounded by water, and the proximity of water helps in development of industrial regions, because you can get the water practically very easily from this proximity. The dock or the port facilities help in bringing the raw materials for the industries, and the finished products can be shipped out of these areas. So this is an existing map of what exists in that region. So typically how we do industrial ecology approach is that we look at a plant area or an industrialized area as a whole, and imagine that there is no boundaries existing between these industries. There are plants that exist currently, and then there is a fresh resource use that is coming into the system, and there are wastes that are generated from the system. Now, the concept of industrial ecology lies upon the fact that there may be centralized mixing and interception systems that can be developed so that we create value for all the industries, and we have like centralized resources which minimize some of the costs of each of these industries. And here I give an example of these existing industries. Let's say we have Haldia Petrochemicals, Haldia Energy, Indian Oil Corporation, and Exide. These will be the anchor plants, which are the major plants in the region. And that is why I mentioned the anchor tenant approach. These will be some of the major plants in the region which will have their own facilities for mixing and interception. And they also probably serve their own needs. For example, maybe Indian Oil's output becomes an input for Haldia Petrochemicals, and also the energy from Haldia Energy Limited may be supplied to Haldia Petrochemicals. I'm just using this as an example. It may not be the existing case, but this is just used as an example of industrial ecology approach. And then there can be new industries which will be dependent on existing infrastructure, which is these existing bigger plants, which are the anchor plants. And these new industries will become tenant plants, where you can have these, because these new industries have a period of growth and period of their break-even period. They will be supported by the centralized systems, and they can be using some of the existing resources in an industrialized region, where they can then benefit from some of these centralized systems. But we have to do this in a very systematic manner so that we know exactly where these cannot grow organically. We have seen organically grown industrial regions, but primarily organic growth is good, but it is also important for us to systematize these entire regions so that we have economic benefits as well as environmental benefits that are created for the overall region as a whole. So here I show a potential sustainability map for water management. So if you remember the original systems view of sustainability, we have here economic capital and social capital and environmental capital or natural capital, where we have extraction of water for industrial development, not going into the societal development water extraction, because that is also a way, but this is only showing the industrial interactions at this stage. So there are wastewater generated from the industry, which can potentially impact waterways and agricultural land. If you go back to the Haldia region map, on the far left corner, you'll see that there is agricultural land, and if there is potential of waterways polluted that flow into agricultural land with the industrial discharge, it may get into our food system. So it is important for us to measure how these wastewater is discharged and where this is discharged. And wastewater can potentially impact humans and livestock. And we do have economic value creation for the society through jobs creation and other activities and the products that are created from the system. One major thing that I would like to mention here is that related with the environment, very much related with the environment, are the proximity of the Haldia region to the Bay of Bengal area, where storm surges resulting from storms are common, becoming quite common in recent years, as well as the mentioned quality of salinity of the water in the region, which is, these two are very important issues that need to be tackled for any climate related changes in the future. So that those stormwater and storm surges can also impact not only the industrial activities in the region, but also the agricultural activities in the region. So whenever any water planning or management needs to be done, those climate change related conditions need to be taken into account while we do this entire water map. Now, as here for again purposes of understanding, we have to have industrial investment for pre-treatment of the water. We have to have investment for discharge control, and we have required energy for water pre-treatment or treatment, and we have to also meet the government imposed regulations for discharge limits. And these translate into corporate social responsibility that we have heard of, and minimal impact on the environment, and take advantage of existing industries in the region with low-grade energy recovery, and maximize profit or minimize costs of energy using cleanups, energy use, cleanup, or litigation fees that can arise from this. So this is an example of process integration method that we use. So typically we draw the entire system input and output of water. And again, most water treatment or water management within an industry is done on an input basis and an output basis, but seldom is the whole water balance done. So this is an example of a pulping process, paper pulping process, where we have all the inputs and the outputs. And then we show through mathematical modeling and integration that I'm not going to go into the details of, on exactly how much we can recover or recycle through a recovery network. So here we look at the different inlets of water, we look at the outlets of water, and we have a recovery network model which can recycle some of this water. And then we have different stages of recycle. We have a freshwater target, and we have a current usage. So through this mathematical integration and process integration methods, we can reduce our current usage from 52,000 gallons to 9,800 gallons of water. So this is just an example to show how these mathematical integration techniques can work in practice to actually reduce. And this is from an actual plant in Georgia. So just as closing thoughts, relevance to COVID-19, we have renewed discussions on future of work and specifically moving to digital twins or Industry 4.0 efforts. So such models in Industry 4.0 type of work require models of in-depth understanding that can help in transitioning to this Industry 4.0. Sometimes they can be people agnostic processing and plant operations, which will ensure that people are safe and they do not have to come to work and they can do a remote location plant operation. And it can be used for planning for new technology development as well. So anything that that we have faced during the COVID-19, one thing that has come out is that process industries such as petrochemicals or refineries are a little bit behind in terms of Industry 4.0. We are at the forefront of research in these areas, and we work with probably all of the major oil giants in the world. And this is something that observe that the process industries in particular, need to be ramping up their efforts, and modeling tools and capabilities like this help in that regard. Of course, holistic approach to mathematical methods. We want to view the Haldia industrial belt as a holistic system with industries, people, and environment as joint stakeholders. We can have more stakeholder engagement through industries providing high-level industrial data that can be used for such model building and analysis. We do not have to go into their plant boundaries. We can look at the overall system as a whole. And these can be used for policy making and analysis, where commonly shared goals of environmental management, such as protection of water, air, and land, can be realized. we can work for future workforce development, which is very important given the digital divide and all the implications that the students have faced in current scenario, where industry academia collaboration models can help in technology transfer, analytical methods, and training the students for future workforce. And as enablers, BCCI can provide the ideal platform and play a pivotal role for integrated system studies, policies, and investment plans in the Haldia region, with potential of building such models for any industrial zone in India. With that, I would like to let you all know that Bengal Chamber of Commerce and Industry and Texas A&M University has signed a memorandum of understanding to work together in the Bengal region, and we would welcome any collaboration through the mechanism towards industrial and ecological sustainability. And I have my contact here, so if anybody is interested, I'll be happy to get in touch.
Thank you very much, Dr. Sengupta. In fact, it's a very comprehensive presentation, quite insightful, and definitely the industries who are participating in today's program can take the benefit of your knowledge and resources if they want to improve their existing system and process in their endeavor for sustainability. So far, my knowledge goes that the mathematical model of mass balancing is naturally done for any petrochemical industry or any large water consuming industry, as a matter of fact, in the design phase by the consultants, reputed consultants in the world. But that is done at the time of putting up the plant. But what is interesting is that an existing running plant can still utilize this same model and find out the ways and means how they can improve it and optimize the resource cost. So that's very.
I would like to interrupt you in one thing. So this is not our traditional mass balances. So this is mass integration. So the difference between a mass balance and mass integration is that we have these set of balancing that needs to be done. And that is where our input and output balances need to be made, not in terms of just mass balance, but we also use these methods for mass and energy nexus, water energy nexus. And that is where, I mean, it can be, we can look at things as either a set of equations, or it is also like allowing us to play with the ranges where our constraints come in, and that is where the optimization comes in. So mass balances are typically our like balance equations, which are, we have a particular set of variables and we have an exact set of equations where we have to solve. But optimization provides us the bandwidth to play with and get to other alternate scenarios and solutions. So I think integration in itself is very powerful, where we do property integration. Property integration is one of the biggest and most difficult challenges in integration. With heat integration, we are used to doing pinch analysis type of activities. But when it comes to properties, we have multiple variables. With heat, we are just dealing with one variable and one property, which is the thermal capacity. But in property integration, we have these different properties. It can be density, it can be your content of TDS, it can be concentration, it can be anything. So property integration and multiple property integration becomes a very difficult and tough challenge. And that is why it still remains one of the biggest issues in implementing in large scales. But having said that, we have used these methods for several sustainability solutions, and One thing that we have found is that if industries are interested to work with us, then I think we can realize much more through the powerful mathematical tools. It's also very important for training the next generation of students. That is our goal. Like being in the academia, our goal is to train the next generation of students.
Yeah, I agree with you. In fact, your example of craft, where the water consumption had come down from 45,000 to 9,000, the saving of in the cost of water itself will be huge, which can improve their profitability, their competition strength, and everything. So
exactly, and the craft process, I think the craft process is a very good example where property, because whenever we are using fresh water and we are treating the fresh water, we are having a cost, and we are discharging the water and we are having a cost for disposal there. But the quality of the water is not as bad, and it can be directly recycled with very minimal treatment. So the cost of treatment in that section is way less than the inlet water treatment and the disposal cost. So it is, but this cannot be done intuitively. We cannot do this sort of analysis intuitively, because we have to look at the properties of water and match the property of water within the system. And that is where I think like it becomes a little bit cumbersome for industries as a whole, because the water pre-treatment and the water disposal are handled by different entities sometimes. They are not handled by the same entity within an industry. So the bottom lines for the two groups may be different, but that's why this needs to be implemented from a management level, where the management puts people to look at both inlet and outlet and qualities, and kind of like balance between the inlets and outlets. So yeah, so that is where I think the craft process is a very good example that we use for this integration method.
Yeah. In Calcutta, there is a ITC plant, Triveni Tissue. They had implemented similar approaches for cutting down the cost of pulping production by recycling the water from the pulp process to the pulping section. Thank you very much, Devolina. May I now request our observer, Dr. Padmavati, followed by Professor Banerjee, to come in and share your observation, 2 minutes each.
Well, I think it's been a very exhaustive session so far as the looking at the entire gamut of the looking at industry compliance on one end and looking at the far-reaching effects so far as biodiversity and in the larger context, the environment itself. I think it will not be wrong to mention that West Bengal has the largest wetlands, and that is something which we prize it as a state. Ultimately, if you really look at an overall gain, I think we should look at what is the kind of overall gain that we are giving to the wet bodies. And because that is where we see the greatest limiting of resource that we see in future. So certainly they're interlinked, and so therefore we are also concerned about biodiversity, and we are also concerned about health as a paradigm. When we say health, the health of the environment, I think should be the primary concern, because we are part of the environment. So given that, I think, how do we really look at, I think I appreciate Dr. Sen Gupta, it was really good to hear you in terms of your research, and we really need to look at an interconnected way of looking at implementation of things, because we do work in a very disconnected way. Industry brings in certain changes, but cannot look at all changes to be implemented. Now there are agencies who are doing treatment, who are coming up with test studies. They're at one end. So we need a kind of an integration and channelizing of information. And then we have agencies. We have BCCI, who is, I would believe BCCI is the one which will take care of that integration part of it. So we need a kind of a system where there's free talk happening, and we can have a lot of hand holding and build a lot of interlinkages. So if you look at that, Haldia should be looked at as an ecosystem. Haldia ecosystem in a period of time, let's say pre-COVID, post-COVID, and what is the post-COVID plan? I think outlining that is the fundamental thing, which this, I would believe, this serious deliberation should look at. That how do we really need to look at situational issues? How do we need to look at the larger context of even the ecosystem? So we need to build that kind of overall perspective. So certainly the COVID has put us into a necessity scenario where we need to implement urgent implementation. But tomorrow, post-COVID, are we going to behave in the same way and look at environment as an urgent need? Because there's always this slipping back. So to what extent we are really going to reach that that gap is something, and this is where, of course, we come from the academics to tell you, but I think the more linked we are with respect to our goals, with respect to environment, I think we are closing the gap. And the overall gain should be on to what extent we are actually coming back to the near normal so far as the Haldia ecosystem is concerned. And that, I think, will be, which will mean localizing the climate goal in the total. So I know it's a lot of wishful thinking, saying this is much easier than, but we need wishful thinking. We need that kind of ambition. Today, people are talking about climate ambition. So we need that climate ambition. And the Haldia ecosystem must look at a combined climate ambition. Today, we heard individual industries. Now, these set of industries should come with a joint plan for the Haldia ecosystem. And these are the words I just have as a academician, and who along with others, believe that we need to restore back.
Thank you. Thank you very much, Dr. Bhatt. May I now request Professor Banerjee to come in? Hello, Professor Banerjee.
I think there is a disconnect issue, sir.
Okay. So in that case, let me conclude. In fact, with all the comments what we have, and from all the participants and the expectation, the objective of organizing this program is already satisfied. Our intention of organizing this program is to initiate thought processes in the mind of the stakeholders of what more can be done, what are the opportune areas, and how those areas and those opportunity can be exploited. We definitely, from Bengal Chambers, we are going to monitor the development in this Haldia region as a part of our ongoing activity. And when we meet next year with the much improved situation, or I'm sure there will be lot of improvement, lot of good news on the table. Thank you very, very much. And to all the participants, to all the speakers, and our secretariat members headed by Angana, organizing this excellent program. Thank you.
Thank you, sir. And we wanted also to make it a stakeholders consultation roundtable wherein we would have stakeholders' views other than that of our lead stakeholders as in the speakers. Shuchishmita, who's kind of coordinating this program, would connect with each one of the participants, seeking in case they have something to connect with the speakers, they may send to Shuchishmita. She will set up a, date deadline. And collating the, your queries, she will connect with the speakers and revert back to you. Thank you.